In this video, I'm finishing section 2.7 on graphic techniques. So we have been working with transformations of functions. Okay, so far we have done. We have studied the following transformations. We did translations, or shifts, okay, so the translations we did, let's call them 1A, were vertical shifts or vertical translations and horizontal translations. And we did reflections. Okay, so we did reflections across an axis and reflections across the origin. And one good observation was that if a graph is, well, actually we did, okay, reflections across an axis, reflections across the origin, and we did symmetry. Well, let's see. Okay, actually we didn't do that. We did symmetry with respect to an axis and symmetry with respect to the origin. So if a graph is symmetric with respect to both the x-axis and the y-axis, the graph is going to be symmetric with respect to the origin, but not necessarily the other way around. A graph might be symmetric with respect to the origin, but does not have to be symmetric with respect to the axis. Okay, so a continuation of that, of reflections, is even and odd functions. Okay, so I'm going to copy the definition from page 266. Okay, so that's on page 266. A function f is an even function if f of the opposite of x equals f of x for all x in the domain of f. That is, the graph is going to be symmetric with respect to the y-axis. And a function is an odd function for all x in if f of the opposite of x is the opposite of f of x for all x in the domain of f. That is, the graph is symmetric with respect to the origin. So an even function is symmetric with respect to the y-axis, and an odd function is symmetric with respect to the origin. So in this example, we will determine whether each function is even, odd, or neither even or odd. The first function is 2x cubed minus 3x. Okay, so we are going to evaluate f at the opposite of x. If I obtain again f of x, the function is going to be even. If I obtain the opposite of f of x, the function is going to be odd. And if I don't obtain f of x or the opposite of that, the function is neither even nor odd. So this is what? This is 2 times the opposite of x raised to the third power minus 3 times the opposite of x. Okay, so the opposite of x raised to the third power is the same as the opposite of x cubed. That's because minus times minus is plus, and plus times minus is minus. And x times x times x is x cubed. And then minus times minus is plus. So 2 times the opposite of x cubed is the opposite of 2x cubed plus 3x. So if you compare it to the original function f of x, we actually have that the terms have opposite signs. So this is going to be the opposite of f of x. Okay, so this function is odd. Number 2, we're going to do the same for f of x equal to 2x to the fourth minus 8x squared plus 3. So to determine whether the function is even or odd, we're going to evaluate f at the opposite of x. So this is 2 times the opposite of x raised to the 4th power minus 8 times the opposite of x squared plus 3. But the opposite of x raised to the 4th power is going to be x to the 4th power. Minus times minus is plus, times minus is minus, times minus is plus. Then the opposite of x raised to the 2nd power is going to be x squared plus 3. And I'm missing an 8. So we actually have the exact, we actually have the same function we began with. And because of that, f is even. In part C, we will determine whether f of x equal to x squared plus 2x plus 1 is even, odd, or neither even nor odd. So we're going to plug in the opposite of x. So this is the opposite of x squared plus 2 times the opposite of x plus 1. Okay, the opposite of x raised to the 2nd power is x squared, but 2 times the opposite of x is minus 2x. Okay, so here, the first and the last terms have the same sign, but the second term has, the second terms have opposite signs. So this is not equal to f of x or the opposite of that. So this is not equivalent. So f of the opposite of x is not equivalent to f of x or the opposite of f of x. So the function is neither even nor odd. Thus, f is neither even nor odd. Okay, so we have done translations of functions, translations of graph. vertical and horizontal translations. We did reflections. And in the process, we studied symmetry and whether a function is even or odd. So that has to do with reflections. And the last type of transformation is going to be stretching and shrinking. Or stretches and compressions. We're going to have just like translation, we're going to have vertical stretches and shrinks and horizontal stretches and shrinks. So we will consider okay, so we consider f of x equal to x squared. And let g of x be 2 times f of x, or 2 times x squared. We're going to make a table and compare the graphs. Okay, so I'm going to make a table with 3 columns. Yeah, it's not letting me undo. So now I have to delete it. But we're going to make a table with 3 columns. One with x squared, which with the squaring function, which we have done several times, and 2 times the squaring function. Our values are -2, -1, 0, 1, and 2. And that's something we have done several times. The y values are 4, 1, 0, 1, and 4. So 2 times x squared, we're going to multiply the number in the middle column by 2. 2 times 4 is 8. 2 times 1 is 2. 2 times 0 is 0. 2 times 1 is 2. And 2 times 4 is 8. Okay, so let's put this together. Okay, the first function is x squared. Okay, so this goes through the points 0, 0, 1, 1, 2, 4, -1, 1, and 2, 4. So this is the graph of x squared. And the graph of 2x squared. This passes through -2, 8. -1, 2. 0, 0, 1, 2, and 2, 8. So, and this is the graph of 2 times x squared. So at the end, yeah, I have some extra line. Okay. Yes, I'm going to fix this. Okay, so the graph of x squared is stretched vertically by a factor of 2. Or the graph of f of x, or the graph of g equals 2 times f of x. Is the graph of f of x vertically stretched or stretched vertically by a factor of 2. And we are going to let next situation, we will let h of x be 1/2 f of x. So that is going to be 1/2 x squared. So for that, I'm going to make, well, I can make 2 tables. Well, I'm going to use the same values. So I'm going to make a table with 3 columns. Okay, we know the values. And 1/2 x squared, y equals 1/2 x squared. That means y is going to be half of the value, in the middle column. Half of 4 is 2. 1/2 times 1 is 1/2. 1/2 times 0 is 0. And then we have 1/2 and 2. And this is what I'm going to do. I'm going to copy this graph with it and compare the 3 graphs. So we're going to copy all that. Okay, so the third graph is going to be the graph of 1/2 x squared. So that one goes through the points -2, 2. -1, 1/2. 0, 0, 1, 1/2, and 2, 2. And I could even do things like 4, so something like 4/8 or 4. Let's see. So 4, that's 16. Okay, I'm not going to go that far. But you have an idea of what the graph, what the graph is going to be. And at the end, the graph of h of x that we define this to be, well, I'll have to write a separate note. The graph of h of x equals 1/2 f of x is the graph of f of x. vertically shrunk or compressed by a factor of 1/2. Okay, so in general, I'm going to copy the situation with stretches and shrinkings. That's actually the first transformation that the book does. I did it last. And it's on page 261. Okay, we first have vertical stretching and shrinking. Suppose that A is positive. So if a point xy lies on the graph of f of x, of y equals f of x, then the point x, comma, a times y lies on the graph of y equals a times f of x. If a is greater than 1, the graph of a times f of x is a vertical stretching of the graph of f of x. And if a is positive but less than 1, then the graph of a times f of x is a vertical shrinking of the graph of f of x. And I'm going to add one more thing. So also, if a is negative, then the graph of y equals a times f of x is vertically stretched or shrunk, but it's also going to be reflected. Across the x-axis. Okay, so we did vertical stretchings and shrinkings. This, by the way, on page 261. And we also have horizontal stretchings and shrinkings. So that's what we're doing next. So we're going to let f of x be the square root function. So that's a new example. So let f of x be that, and g of x is going to be f of 2x. So we are multiplying the input x by 2. Or if f of x is the square root of x, g of x is going to be the square root of 2x. Okay, so for that, I'll need to make two separate tables. So we're using for the square root function, we're using the x values 0, 1, and 4. The y values are 0, 1, and 2. But if y is the square root of 2x, so we're going to choose the x values. So the square root of 2x is an integer. We still have 0, 0. But in the next one, we're going to let y be, we're going to let x be 1/2. Because 1/2 times 2 is 1. And we're going to let x be 2, because 2 times 2 is 4, and the square root of 4 is 2. Let's put the graphs together. Okay, so the original function, f of x, passes through 0, 0, 1, 1, and 4, 2. Then the square root of 2x passes through 0, 0, 1/2, 1, and 2, 2. I'm going to use a different color. Passes through 1/2, 1, and 2, 2. Okay, so that's going to be a vertical stretching, but it's also a horizontal shrinking. So the graph has been horizontally shrunk or compressed. And with the basic functions we have been doing, usually a vertical stretching involves a horizontal shrinking and the other way around. A vertical shrinking involves a vertical stretching. So the graph of g of x equals 2 times f of x is the graph of f of x. Horizontally shrunk by a factor, in this case, 1/2. So I'm not going to type that. But on my method, you'll have to indicate the factor. And last situation is h of x. So last situation is a horizontal stretching. So let h of x be f of 1/2 x. So that is going to be the square root of 1/2 x. Or you can write this in different ways. You can also write this as the square root of x over 2. So again, that's an example. We're going to make 2 tables. The first one with the square root function, and the second one with 1/2, the square root of 1/2 x. Okay, so we want to get integers. So I still have 0, 0, but if I want the second point to be an integer, I'm going to let x be 2, because 2 times 1/2 is 1. And the second point is going to be 8, because 1/2 times 8 is 4. And the square root of 4 is 2. So we're going to plot h of x. We're going to graph h of x. Okay, so h of x passes through the graph of h of x, passes through 0, 0, 2, 1, and A2. So that's the graph of 1/2 times x. And the graph of h of x equals f of 1/2 times x is the graph of f of x stretched horizontally. So it was vertically shrunk, but it's also horizontally stretched. And here's the summary of horizontal stretching and shrinking. That's on page 261. So suppose that A is positive. If a point xy lies on the graph of y equals f of x, then the point x over a comma y lies on the graph of y equals f of a times x. If a is between 0 and 1, then the graph of y equals f of ax is a horizontal stretching of the graph of y equals f of x. And if a is greater than 1, then the graph of y equals f of ax is a horizontal shrinking of the graph of y equals f of x. And I'm going to add one more thing. If a is negative, then the graph of f or y equals f of ax is a horizontal stretching or shrinking of the graph of f of x and a reflection across the y-axis. Okay, so I'm going to read the summary of transformations that we did. Okay, so in the description that followed, assume that A is positive, H is positive, and K is positive. In comparison with the graph of f of x plus K or f of x minus K is going to be a translation. Up if K is positive and down if K is negative. On the other hand, if H is positive, the graph of y equals f of x plus h is going to be a horizontal shift. To the left if H is positive and to the right if H is negative. And we did the stretchings and shrinkings. If you multiply f of x by a, then you're going to have a stretching or shrinking. So it's going to be a stretching if a is greater than 1, and a shrinking if a is between 0 and 1. If you multiply the input by a, then the graph will be a horizontal stretching of the graph of f if a is between 0 and 1, and a horizontal shrinking if a is greater than 1. The graph of f of the opposite of f of x is going to be a reflection across the x-axis, and the graph of f of the opposite of x is going to be a reflection across the y-axis. So I will finish with some examples of using more than one transformation. Example 1. Is g of x equals the square root of the opposite of x plus 2. Okay, so we have a set of transformations. The graph of f of x, the graph of the square root function, is, we have two transformations. We have, with this minus sign, we have a reflection. So that's going to be a reflection across the y-axis. And is going to be shifted 2 units upward. The basic function is the square root of x. The new function is the square root of the opposite of x plus 2. Okay, so the graph is reflected across the y-axis. The x values are going to change sign. And if the graph is shifted 2 units upward, the y value, we're going to add 2 to each y value. Let's sketch the graph. We're going to do those together. Okay, so the square root of x passes through 0, 0, 1, 1, and 4, 2. And the graph of the square root of the opposite of x plus 2 passes through 0, 2, negative 1, 3, and negative 4, 4. Okay, so you can see that the graph has been vertically shifted 2 units up and reflected across the y-axis like this. Oh yeah, this doesn't. Yeah, today this tablet is not letting me undo things. Okay, and I'm going to show you an example of how this works, how it is going to work in the homework. If you haven't attempted it yet, I just need to open the assignment to show you how you do this type of problems. Okay, so I'm trying to find one of these examples. Okay, so let's say this one. Now you may know that the graph of x squared has been shifted 7 units left. Okay, so we're going to use the squaring function. Let me see. So if it was shifted 7 units to the left, the vertex is going to be at negative 7,0. Okay, so that's the function. Well, actually, you don't even need to do that. You can just say that the vertical shift. So there is no vertical or horizontal stretch. That is, the factor is going to be 1, but the horizontal shift is going to be 7 units to the left. And there's no reflection. Okay, so save that, check answer, and that's correct. Now this one, we have the opposite of x plus 4 raised to the third power. So that's going to be the cubing function, x raised to the third power, that was reflected across the x-axis and shifted 4 units to the left. Okay. And I'll do one more, preferably one that involves several transformations, or that involves different types of transformations. Let's see. Well, I don't see anything that involves all types, but let's try that. The function is 3 times x minus 4 squared minus 6. The basic function is x squared. So the graph has been vertically stretched by a factor of 3. And it's been shifted 6 units down and 4 units to the right. There's no reflection of any type. So let's save this. And that's it. Okay, so let's go back. I'll do 2 more examples. The next example is number 2. And our function is h of x equals the opposite of the absolute value of 2x plus 8 minus 5. Now you observe the following. Everything is divisible by 2, so this is the same as 2 times x plus 4 minus 5. So we can factor out this 2. So the graph of f of x, or the graph of the absolute value function, Our basic function is the absolute value function, and this is reflected across the x-axis because we had that minus. It is also vertically stretched by a factor of 2 and is then shifted or translated 4 units to the left and 5 units upward. Oh, sorry, downward. Okay, so we'll see what this looks like. I'm going to make again 2 tables. So we have been working with this set of values and the new function. Okay, so this was shifted 4 units to the left. So 4 units to the left, we're going to subtract 4 from every x value. -2 minus 4, -1 minus 4, 0 minus 4, 1 minus 4, and 2 minus 4. So also, this was shifted 5 units downward. So this passes through. 2 times -4 is -8. -8 plus 8 is 0. 0 minus 5 is -5. Then 2 times -3 is -6. -6 plus 8 is -2. And -2 or -6 plus 8 is 2. The absolute value of 2 is 2. So that's -2 minus 5 is -7. Then 2 times -2 is -4. -4 plus 8 is 4. The opposite of that is -4. Minus 9 is minus 5 is -9. 2 times -5 is -10 plus 8 is -2. The absolute value of -2 is 2. And the opposite is -2. -2 minus 5 is -7. And -6 times 2 is -12 plus 8 is -4. The absolute value of -4 is 4. The opposite of that is -4. -4 minus 5 is -9. Okay, so we are going to finally compare the graphs. Okay, so I'm trying to find some space. Okay, so x values, we got them from -6 to 2. And then we have this all the way to -9. Okay, so let's sketch the graph. The first graph, we have done this a few times. That's the graph of the absolute value function. And the graph of the new function, it passes through -6, -9, -5, -7, -4, -5, -3, -7, and -2, -9. And the last one, the last example, with this I'll finish the section of transformations. That was number 3. It's k of x equal to -1/2 times x squared plus 2. So the graph of the squaring function is okay, we have this minus sign that involves a reflection. So the graph is reflected across the x-axis. It is vertically shrunk by a factor of 1/2. And shifted 2 units upward. That's coming from that positive 2. Okay, so let's make the two tables. Okay, one we have, we already know. And the other one, our new function. This is the opposite of 1/2 x squared plus 2. So that was vertically shrunk by a factor of 1/2. So we're going to multiply each x value by 2. That is, I'm not going to take x equals 1 because I don't want any fractions. I can start with 0, that's fine. 0 times whatever is 0 plus 2 is 2. But the next one, I'm going to choose -2 and 2. So I don't have to plot any fractions. So -2 squared is 4. 4 times -1/2, it's -2. -2 plus 2 is 0. Same with 2. 2 squared times -1/2 is -2 plus 2 is 0. And the next one, I'm not choosing 3 because I'm going to have a fraction. I will let x be 4 and -4. So that way we have points with no fractions, with integers only. 4 squared is 16. 16 times -1/2 is -8. -8 plus 2 is -6. And same with -4. So I'm just going to draw the graph of the new function. So I'm almost done with this. Okay, and let's plot the points. Okay, so this graph goes through -4, -6, -2, 0, 0, 2, 2, 0, and 4, -6. So you know the graph of y equals x squared well enough. I'm just doing the graph of the new function. So that's the graph of the opposite of 1/2 x squared plus 2. Okay, so this is it. With this, I finish the 7th section on chapter 2. Thank you for listening.